All right, class, this is we're moving into chapter 3. How exciting. We're going to talk about acceleration and accelerated motion. Chapter 3 has 4 sections. Most chapters in this book have 4 sections. The first section has to do with acceleration. We got to define it. And we're trying to learn how to calculate, represent graphically the acceleration of an object in one dimension. We're only going to be in one dimension for now. I can interpret graphical representation of velocity versus time curves, which is different than what we did last chapter. We were in position versus time curves of an object that's in motion. So let's just think about a generic situation. Every time an object starts, stops, turns, speeds up, and slows down, the velocity is changing. Let's recall some things about velocity. What is velocity? It's a vector. It has a magnitude and it has a direction. So anytime I change the speed of my car from 5 miles per hour to 10 miles per hour, I've actually changed the velocity, okay? But this is something that most people don't think about. I also change the velocity of the car when I turn, because velocity by definition has a direction. So even if I maintain a constant speed while turning, my direction's changing. So something's actually causing that velocity to change. All right, so acceleration is the rate at which the velocity changes with time. So if the velocity changes, whether it's the magnitude or the direction, acceleration has to be present. So I'm going to reiterate this point a few times. So velocity changes when the speed changes. So 5 miles per hour to 10 miles per hour. Velocity changes when the direction of the object changes. So even if I'm going at 5 miles per hour and I make a turn, what happens? My direction changes. So by definition, if velocity includes a magnitude and direction, the velocity is changing even though my speed is the same. That's kind of hard to think about, but maybe you've heard of this thing called centripetal acceleration. That's what's actually happening. Anyway, so let's again reiterate this. 3 ways a car can accelerate. Love it if you paused it and try to figure it out yourself. 3 ways. I can speed up. I can slow down. And I can turn. So if I'm driving in a circle at 10 miles per hour, even though I'm at a constant speed, my direction is constantly changing, I must have an acceleration there, okay? And although we don't spend too much time in this class talking about centripetal acceleration, AP Physics absolutely does. Definition of acceleration, so let's define it. Acceleration is the rate, so some magnitude over time, at which velocity changes with time. So what is velocity? Meters per second with time. So we're going to quickly see what that unit is. So acceleration like velocity, this is super important. Acceleration like velocity has both a magnitude and a direction. So acceleration is a vector, has magnitude and direction. So we have 2 different types of physical quantities in this class. We have vectors and we have scalars. Scalars have no direction, and such as time, for example, it has no direction. It doesn't make any sense to say it took me 5 hours to the east to do something, okay? But it does make sense to say that I accelerated in the positive direction or I accelerated in the negative direction. So acceleration does have a direction, okay? So what is the definition of acceleration? So it is the change in velocity over change in time. So let's just do a unit analysis. So I have change. What does that change mean? That's that delta symbol, okay? And if every time we have that delta symbol, if I want to know the change in something, I take final minus initial. So in units, I have velocity, which is in meters per second, divided by second. So Mrs. Query's little table, I have meters per second, and I divide by a second. What are my units? Meters per second squared. This is an acceleration unit. and you can see it right here. So we're going to keep things in meters and seconds, and if you're solving for an acceleration, your answer better be in meters per second squared, or else something's wrong, okay? Or you lose points for one thing. All right, let's do, so there's our definition. Delta V over delta T is the average acceleration. Oh, by the way, different ways to average can be displayed like this. Average also, you might see things with a bar over it. That's what the average, that bar means average. All right, so let's do a problem. A cyclist accelerates by increasing his speed 2 meters every second. 2 meters per second every second. After 1 second, his speed is 2 meters per second. After 2 seconds, his speed is 4 meters per second, and so on, as displayed in the figure. Calculate his acceleration as requested below. Well, I actually don't even need to do this problem. I can actually look at this right here. I changed my velocity 2 meters per second every second. That gives me 2 meters per second squared. So there is his actual acceleration. But let's just go through the exercise to get some practice. What am I asking for? Calculate his average acceleration as indicated below. So let's just use our equation. So I have average acceleration, change in velocity over change in time. What is change? Final minus initial over t final minus t initial. So let's go look at x equals 0. I see that I have this time at x equals 0 and a velocity. So I know that v initial was 0. V final, let's go look at that. We're at 1 meter, so I'm at 1 meter. So here's my data at 1 meter. V final is 2 meters per second. T final was 1 second. T initial was 0. So this is a simple plug and chug, I hope you think that. 2 meters per second minus 0 over 1 second minus 0 gives me 2 meters per second divided by 1 second gives me 2 meters per second squared. And there is my answer. All right. How about between x equals 1 and x equals 4 meters? So here's my initial, here's my final, here's my initial data. I'm sorry, I was backwards. 4 meters is the final location, 1 meter is the initial. So let's write our information that we have. We know that the final is equal to 4 meters per second. The initial is equal to 2 meters per second. T final was equal to 2 seconds. T initial was equal to 1 second. And then I can just use my equation, which is V final, 4 meters per second minus 2 meters per second divided by 2 seconds minus 1 second. And that gives me 2 meters per second divided by 1 second, 2 meters per second squared. Okay. Next, let's do some pink. We have between x equals 4 and x equals 9. So here's 9 meters. Here's my final location, and this will be my initial location for that problem. So I know that the final is equal to 6 meters per second. The initial is equal to 4 meters per second. T final in that second or situation was 3 seconds. T initial was equal to 2 seconds. Notice the elapsed time is 1 second, so you could just say T equals 1. But at any rate, average acceleration, V final, 6 meters per second minus 4 meters per second over 3 seconds minus 2 seconds is equal to, once again, I have 2 meters per second, and I got to divide by 1 second, and I get an answer of 2 meters per second squared. Why am I doing this right here? I'm showing you how to make sure your units work. Okay. All right, let's do the last one. We'll do that one in this weird blue color. I don't know what that is. And so here is my final location, and they're asking compared to my initial location. And so let's get our data all lined up. The final is equal to 6 meters per second. T final is equal to 3 seconds. The initial was 0. T initial was 0. The average acceleration is equal to 6 meters per second minus 0 over 3 seconds minus 0. I get 6 meters per second divided by 3 seconds, which gives me 2 meters per second squared. Okay, so there is some practice. Now let's do some more. Now, this entire physics course is just nothing but one word problem after another. And the thing that I would advise is for you to read the word problem in its entirety, go back and reread the word problem and outline and circle things that the word problem gave you that you will need. Okay, so let's read the entire problem. An advertisement says a car can go from 0 to 26.8 meters per second in 6.2 seconds. What is the average acceleration of the car? A drag racer deploys a parachute and slows down from 130 meters per second to 45 meters per second in 3 seconds. What is the acceleration of the racer? So I have two problems here. So let's read again part A. An advertisement says the car can go from, this is important, so let's underline that. And what is that? Well, this is my initial velocity. This is my final velocity. And what did this value give me? This was the time it took to go. So that's the elapsed time, okay? So I want to know what? What are they asking? They want to know the average acceleration. So for A, I would come over here and I would actually write that. B, and this is how we show work, people. B initial is equal to 0. B final was equal to 26.8 meters per second. The elapsed time was given to me at 6.2 seconds, and they asked for the acceleration question mark. Now I have an equation that I have been given for acceleration. There is my equation without numbers. And then I will actually plug in numbers. I will then solve the problem, which I've already done, and I will find that to be, and just to show you, 26.8 meters per second divided by 6.2 seconds. Notice my units, I get meters per second squared. Fantastic, that's what I want. 4.3, two sig figs if I really wanted to pay attention, meters per second squared. I'll flip that off. All right, B. A drag racer deploys a parachute and slows down from 130 meters per second. So there's my initial velocity. And to 45 meters per second, there's my final velocity to 3 seconds. There's how much time it took. So for B, I know the initial is equal to 130 meters per second. B final, 45 meters per second. The elapsed time, 3 seconds, and I was asked for the acceleration. So if I just plug and chug, acceleration, the final, the initial, elapsed time, 45 meters per second minus 130 meters per second divided by 3 seconds gives me, that's going to give me a negative 85 meters per second. That's what the top value is, divided by 3 seconds. And I'm not suggesting you have to show me all of these little steps here, this in particular, what I'm doing. I'm doing this to teach you how to see that your units work. And that will give me negative 28.3 meters per second squared. Circle, tell me that's the answer to B. Now, question for you. Does it make sense to have a negative 28.3 meters per second squared? Can I have a negative number for acceleration? Why not? Can't the acceleration be in the negative direction? Sure, it can, because it has both a magnitude and direction. Now let's just go read what's happening. We have a drag racer. He's flying at 130 meters per second, which is pretty fast, by the way, and he slows down. So let's actually visualize what's happening. So here's my car. He's booking it. And so he has his direction of velocity is to the right. This is my velocity. And then all of a sudden he slows down. He slows down. This is 130 meters per second. And now all of a sudden he is slowing down. Well, in order for him to slow down, something has to slow him down. And sure enough, my acceleration has to be to the left. And we're going to talk about that here soon. We're going to learn about this. So velocity was positive. Acceleration had to be negative in order for that car to slow down. Okay. All right. The winner of the drag race. Let me just see. Yep. This is where I'm ending. And then your homework will be to try a problem on your own. All right. The winner of the drag race, shown in figure 3, was traveling with a speed of 140.3 meters per second at the end of a quarter-mile course. The car started from rest and had an average acceleration of 30.4 meters per second squared. What was the winning time for this race? Okay, so we have read the problem. Step 1. Step 2, reread the problem, underline key things. Define what those key things are. The winner of the drag race shown in the figure was traveling with a speed of 143 meters per second. What is that information? That is my initial velocity. At the end of the quarter-mile course, the car started from rest, so I have to go back and change that, but that rest is pretty important. So that is actually, they started from rest, so that velocity that they gave me prior was my final velocity, okay? And he had an average acceleration of 30.4 meters per second squared. There's my acceleration value. What are they asking for? Time. So let's go rewrite all of the information they gave me. So I know the initial is equal to 0. This is a very important word. Let me highlight it in yellow. Rest. That means it's not moving. There's 0 velocity. Its final velocity was 140.3 meters per second. They tell me acceleration is 30.4 meters per second squared. All of those units are beautiful. I don't have to do any conversions. I need to be in meters, seconds, and kilograms in this class, remember? Okay, I want to know time. So acceleration, change in velocity over time, elapsed time. That means the initial was 0. And I want time, so I rearrange that equation, A over delta V, and I plug in numbers. 30.4 meters per second squared divided by change in velocity. Final minus initial, that gives me 140.3 meters per second. Now this is a trick. So if I divide by meters per second, I'm just going to take this little second right here and flip it to the top. And then what happens? Let's do some unit analysis. Meters cancel. One of those squared cancels. Whoops. And I can tell actually I've now got a problem. Let's start over. I can tell just by units alone. What am I trying to solve for? Ah, I see what's going on. See, my units actually told me I had something wrong. I'm tired. I need to rearrange this equation for time. So I multiply both sides by time. Let's just show you how I do that. Multiply both sides by time. Time cancels. And then I should have change in velocity on top, which is not what I had, over acceleration. Units were my guide, and I knew for a fact I was wrong. So what's the change in velocity? V final minus V initial over acceleration. So V final is 140.3 minus 0. And that's in units of meters per second, divided by 30.4 meters per second squared. Now let's look at our units. So I have 140.3 meters per second divided by 30.4 meters per second squared. So take that per second squared and put that second squared up back on top. I can show you exactly why that is mathematically if you need to. The one of the seconds cancels, I'm left with 1 on top. The meters both cancel. Now I have an answer in seconds. That's actually a unit that makes sense. And now I can just do the calculation, click, and I get 4.6 seconds. I'm actually glad I made that mistake. Hopefully you can see why units are so important. Okay, now, that's the end of my lecture today. Again, all we have done now is define what acceleration is and how to utilize that equation to find acceleration. One thing I need to make sure you understand is please pay attention to all of your signs. Since velocity can be negative, acceleration can be negative, follow your, make sure you keep track of the signs of your velocity and acceleration. So look forward to continuing on with this material. We're close to getting into some of my favorite stuff. So that's what I got. Come see me.